Okay, welcome everyone. So in this video, we are going to prove a really powerful theorem about similar matrices A and B and how that relates to the eigenvalues of these matrices. So the theorem states the following, that if we have n by n matrices A and B that are similar, then they have the same characteristic polynomial. And if matrices have the same characteristic polynomial, they're going to have the same eigenvalues because the eigenvalues of a matrix are exactly the roots of the characteristic equation. So if two matrices have the same characteristic polynomial, they have the same characteristic equation, and thus they're going to have the same eigenvalues with the same multiplicities. So let's take a look at how we can prove this really important theorem. So if we take matrices A and B and we assume they are similar, then that means matrix B can be written as P inverse A times P for some invertible matrix P. So let's see how that affects the characteristic polynomial. So to find the characteristic polynomial, we would take the determinant of b minus lambda I. This is if we wanted to find the characteristic polynomial for matrix B. So the matrix b minus lambda I, well, I can replace b with P inverse AP because we have assumed A and B are similar. So that means we can find a matrix P so that we can rewrite B as P inverse times A times P. And we can rewrite lambda times the identity matrix as lambda times P inverse times P, because if we take a product of the inverse of P times the matrix P, by definition, this gives us the identity matrix. So we've done two things in this step. That is, we've used our assumption that B is similar to A, and then we use the fact that if P is invertible, then we can replace the identity matrix with P inverse times P. And this is going to allow us to rewrite this expression by factoring out a P inverse on the left. And what allows us to do that is this second term in the previous expression, the lambda times P inverse times P. Recall, we can multiply this scalar lambda at any point in this product. So this is totally equivalent to saying P inverse times the matrix lambda P. So this allows us to take P inverse out on the left to factor this out from both of the terms in our difference. So we can rewrite this line P inverse AP minus P inverse lambda P by factoring out P inverse and writing this as P inverse times the quantity AP minus lambda P. And then we can do the same factoring out P on the right of this expression. So that means this expression for beta minus lambda I, if B is similar to matrix A, we can rewrite that as the product P inverse times the quantity A minus lambda I times the matrix P. And next, we're going to go ahead and find the characteristic polynomial for matrix B by taking the determinant of B minus lambda I, which we now know is equivalent to P inverse times A minus lambda I times P. So let's go ahead and take the determinant of B minus lambda I, which we now know we can rewrite this as the determinant of P inverse times A minus lambda I times P. And now we can use a really nice property of determinants, namely that if we take the determinant of a product of matrices, that's equal to the product of the determinants. So we can apply that to the product P inverse A minus lambda I P, and therefore the determinant of that product we can write as the determinant of P inverse times the determinant of A minus lambda I times the determinant of P. And next, we can simplify this further because we have shown in the past that the determinant of P and the inverse of P are related by the reciprocal relation. So if we take the determinant of P inverse, that equals 1 over the determinant of p. And now we have this product of three terms, and we can multiply scalars in any order that we like. So taking the determinant of p inverse times the determinant of p would just give us the number 1. And so this product of three determinants therefore simplifies down to just the determinant of a minus lambda I. So what we can see now is that these two characteristic polynomials are exactly the same. So therefore, the resulting characteristic equations for each of these matrices are going to be exactly the same. And therefore, we've proven that if two matrices A and B are similar, then those two matrices are going to have the same eigenvalues with the same multiplicities because their characteristic polynomials are exactly the same.